We have already found that the energy of the hydrogen atom in nth orbit is minus m e raised to the power 4 divided by 8 n square epsilon naught square h square. Suppose electron transit from initial energy state, that is Ni, to final energy state, say Nf, where Ni is greater than Nj. So in this transition there will be the emission of the photon. So we can write energy of the Ni orbit is equal to minus m e raised to the power 4 by 8 Ni square epsilon naught square h square, and Enf of the final energy state, it is minus m e raised to the power 4 divided by 8 Nf square into epsilon naught square h square. Now, because of this transition, there will be the emission of a photon as per the Bohr's third postulate, and this energy of the photon is h nu, and this h nu is equal to E Ni minus E Nf. So it is h nu, that is equal to minus m e raised to the power 4 by 8 Ni square epsilon naught square h square minus of m e raised to the power 4 8 Nf square epsilon naught square h square. Taking the common terms, we have m e raised to the power 4 by 8 epsilon naught square h square. This minus and minus become plus, so we can write it as 1 by Nf square minus 1 by Ni square. Therefore, we can write h into c by lambda, because c equal to nu lambda, that is the speed of light, and nu equal to c by lambda, and it is equal to hc, and 1 by lambda equal to nu bar. This is called the wave number. This is hc nu bar, that is equal to m e raised to the power 4 by 8 epsilon naught square h square 1 by nf square minus 1 by ni square. This implies that 1 by lambda is equal to nu bar, and it is equal to m e raised to the power 4 by 8 epsilon naught square h cube c into 1 by nf square minus 1 by ni square, and this parameter is called Rydberg constant, that is equal to m e raised to the power 4 divided by 8 epsilon naught square h cube c, and its value comes approximately 109677 per centimeter. So we can write that 1 by lambda, and it is the wave number nu bar, it is equal to 109677 into 1 by nf square minus 1 by ni square per centimeter. So this is a formula which we have to memorize. Also, we have to remember the value of 1 by r, and it is equal to 911.5 angstrom. The line spectrum of the hydrogen atom has different series. For example, Lyman series, second is Balmer series, number third Paschen series, number 4 bracket series, number 5 Pfund series. For Lyman series, initial state and final state has some values. If the final state is n equal to 1 and initial state is n equal to 2, 3 and so on to up to infinity, then the series is called the Lyman series. If nf, that is the final state, is n equal to 2 and initial states are 3, 4, 5 and so on to infinity, then we will get the Balmer series. For Paschen series n equal to 3, this is the final state, and initial state has the value 4, 5, 6 and so on to infinity. Bracket series n equal to 4 is the final orbit, and the initial energy state is n equal to 5, 6, 7 and so on. And for Pfund series n5 is the final energy state, and initial states are 6, 7, 8 and so on up to infinity. The region in which these series lies are that Lyman series lie in the ultraviolet region, Balmer series lie in visible region of the electromagnetic wave spectrum, Paschen, Bracken and Pfund series lies in the infrared regions. Here we have to note that if electron transit from n equal to infinity to the lowest energy state, that is say n equal to 1 for Lyman series, then energy difference will be largest. And because this energy difference is hc by lambda, lambda depends on this energy difference, and energy difference is largest, this implies that wavelength will be minimum. Similarly, if n equal to next to the ground energy state, for example for Lyman series, if initial state is 2, this is the Ni and this is Nf, and it transit from Ni equal to 2 to Nf equal to 1, for example for Lyman series, then this delta E will be smallest in comparison to other transitions in same series. So it will be equal to Hc by lambda. Because total energy is smallest, so this implies that lambda will be maximum. So on these facts, there are the number of the problems which we will discuss. Question number 1. In terms of the Bohr radius A0, this is the radius for n equal to 1. The radius of the second Bohr orbit, that is the first excited state of the hydrogen atom, is, we know that radius of the nth orbit in hydrogen atom is n square r0, where r0 is the radius of the first orbit, and it is given here a0. So for first excited state, that is n equal to 2, actually it is a second Bohr orbit, so n equal to 2, r2 will be equal to 2 square into a0, that is equal to 4a0. This is the answer. Second question is, when a hydrogen atom is raised from the ground state, that is n equal to 1, to an excited state, say n equal to 2 or 3 or 4 and so on, its kinetic energy and the potential energy, so we have to check if they will increase or decrease. We know that kinetic energy is equal to half mv square, and v is proportional to z by n, and z is 1 for the hydrogen atom, so this implies that v is proportional to 1 by n. As we move for excited state, this implies that n increases. If n increases, then because v is inversely proportional to n, so v reduces. This implies that kinetic energy, which is equal to half mv square, will also decrease. Therefore, kinetic energy will decrease. Now, we know that kinetic energy is equal to minus of total energy, and potential energy is equal to twice of the total energy. So from this we can conclude that potential energy is equal to minus of 2 of kinetic energy. As we have stated that kinetic energy is decreasing as we move from the ground state to excited state. So 2 kinetic energy will also decrease, and lower the kinetic energy, it means if we take the negative of it, then it means it is a higher value. So we can say potential energy increases. Lesser the negative, higher the potential energy. So we can say that kinetic energy decreases and potential energy increases. Next question is, the energy of hydrogen atom in nth orbit is En. Then energy of nth orbit in singly ionized helium atom will be. We know that in hydrogen or hydrogen-like atoms, energy of nth orbit is proportional to minus of z square by n square. For hydrogen atom, we know that z equal to 1. This implies that En of hydrogen atom will be proportional to minus 1 by n square. Similarly, for singly ionized helium atom, which have atomic number 2, we know that En is proportional to, because z square, so it will be right, it is 2 square by n square. Now we take the ratio of these two. So energy of nth orbit of helium divided by energy of nth orbit of hydrogen will be equal to 2 square. This implies that energy of helium in nth orbit will be equal to 4 times of the energy of hydrogen in nth orbit. Next question is, total energy of electron in first excited state of hydrogen atom is about minus 3.4 electron volt. First excited state refers n equal to 2. Then kinetic energy of this state is, so we have given that energy of second orbit, that is the first excited state of the hydrogen atom, is minus 3.4 electron volt, and we know that kinetic energy is negative of the total energy, so it will be equal to 3.4 electron volt. If we have to ask to find the potential energy also, and potential energy is twice of the E2, so it will be equal to minus 2 into minus 3.4 electron volt, that is equal to, this is 2 into minus 3.4 electron volt, that is minus 6.8 electron volt is the total potential energy.